The 767 is a long-range transport jet. It is one of the most reliable transport jets and provides extended twin-engine operations, or ETOPS, around the world. The 767s in the fleet are part of the large 757-767 family. The crew entry door on the freighter is located as shown. This plug-type door is manually operated from the exterior or interior. It is unlocked, moved inward and upward, and will roll up on tracks in the overhead area. The weight of the door is counterbalanced to reduce the effort required to raise the door. A latch engages to hold the door in the raised position. Inertia reels are installed on the overhead near the 1L door. The cargo compartment doors are shown here. The forward and aft cargo compartments have doors on the aircraft right side. The main cargo door is on the forward left side, while the smaller bulk compartment door is on the aft left side. This frame shows the forward access door and the E&E access door. You can see that one door is forward of the nose gear and the other is aft of the nose gear. This frame shows the location of various antennae on the aircraft. The weather radar antenna is located behind the radome in the nose section of the aircraft. The antenna is a flat dish type, typical for our color radar display. This frame shows the location of the 6 flight deck seats in our fleet. The aircraft is ETOPS equipped for extended range operations and has additional components deemed necessary for ETOPS flights. Additional MEL requirements, crew training and maintenance sign-offs are required for ETOPS flights. The external power receptacle is located as shown. It is equipped with a jack that allows the ground crew to communicate with the pilots through the flight interphone. Pitot static probes and one angle of attack probe are located as shown above. One total air temperature probe is located as shown. An alternate static port area is located as shown. The two 110 cubic feet oxygen bottles provide the oxygen for the 6 masks in the flight deck. The oxygen blowout disc is located on the right side of the fuselage as shown. If this disc is missing, the crew oxygen bottle requires servicing. The cargo compartments are equipped with a smoke detection and fire suppression system. Control of the fire suppression is from the fire control panel on the control stand in the flight deck. Fans normally provide cooling airflow through the equipment compartment. However, an overboard exhaust valve is normally open on the ground and can open in flight to provide cooling when there is a problem with the cooling fan system or smoke requires evacuation. On the ground, the packs can receive compressed pneumatic air from a ground source, the APU, or the engines. For flight operations, the pneumatic air is normally supplied by the engines. Two air conditioning packs are installed. They provide the environmental control for the pressurized portion of the vessel. Ram Air provides cooling airflow over the pack heat exchangers. Shown here is the cooling inlet to and the exhaust from the right pack heat exchanger. Pressurization is normally controlled by one of 2 automatic controllers. Normally, the flight crew sets the landing elevation, and the active controller provides automatic pressurization throughout the flight. Automatic switching to the other controller occurs if one automatic controller fails. In the event of failure of both automatic controllers, a manual pressurization control is installed. The Boeing 767 is powered by 2 GE CF6-80C2 engines. These engines are extremely reliable and have also been used on aircraft such as the DC-10, A300, and L-1011. Each engine has a takeoff thrust rating as shown above. The engine is equipped with the sliding sleeve fixed cascade vane type of thrust reverse system. When the sleeve has moved aft, the fan airflow is diverted forward, but the primary thrust continues to flow normally. Note: the 767 does not perform power backs. The engine overheat and fire detection system detects both overheat and fire conditions and is equipped with a fault monitoring system. The engine fire protection is provided by 2 agent bottles and is controlled from the flight deck. APU and wheel well fire detection are also installed and are controlled from the flight deck. There is 1 agent bottle provided for APU fire protection. There is no active fire protection system provided for the wheel wells. In general, wheel well fires are handled by extending the landing gear. The aircraft is equipped with a left and right AC electrical system. The electrical systems are normally powered by the respective engine generator with bus tie capability. There is no paralleling of the AC systems. Both electrical systems can be powered by APU power. On the ground, both electrical systems can be powered by ground power. The battery standby power system is powered by the aircraft battery. The standby power system provides a limited amount of backup electrical power. For ETOPS operation, the aircraft is equipped with a hydraulic-driven generator, or HDG. The HDG will automatically provide an unlimited source of AC and DC power to certain buses in the event of a failure of both left and right AC systems. Wing anti-ice is applied to the 3 outboard leading-edge wing slats. Wing anti-ice is only operated in flight when required by icing conditions. Engine anti-ice is applied to the engine cowl. Engine anti-ice may be operated on the ground or in flight when required by icing conditions. All flight deck windows are electrically heated. The forward windows have anti-icing protection and anti-fogging, while the side windows have anti-fogging protection only. Operation of the probe heat system is fully automatic. Power to the electrically heated pitot and angle of attack probes is applied anytime an engine is running. Total air temperature, TAT probes, are heated when airborne. The fuel system consists of 3 fuel tanks. Fuel is delivered from these tanks to the engines by the use of electrically powered boost pumps. Center tank fuel is normally consumed first. The center tank pumps are referred to as override pumps since they provide higher output pressure than the pumps in the main tanks. There are 2 AC-powered pumps in each fuel tank. These pumps are normally controlled by switches on the overhead panel. Therefore, the pilots control which pumps are operating to provide fuel pressure to the engines. The center tank can feed both engines and the APU. Each wing tank directly feeds its own engine. However, either wing tank can feed any engine or the APU by use of the fuel crossfeed system. Note: the APU is normally supplied fuel from the left wing tank. On the Boeing 767, pressurized refueling for all tanks is normally accomplished at the left wing. Over-wing refueling is available for the main tanks, but is not normally used. Fuel can be transferred from tank to tank by use of this panel by fueling personnel. For APU operation, the fuel pump activation is normally automatic. For APU start when no AC power is available, a DC-powered fuel pump in the left tank is automatically activated. After APU start when AC power is established, the forward left tank AC pump automatically operates and the DC-powered pump is deactivated. Therefore, the pilots do not turn on fuel pumps for APU start or operation. the aircraft can jettison fuel from the center fuel tank only. Note, it is possible that a full aircraft can remain overweight for landing after jettisoning the center fuel tank. 3 hydraulic systems are installed. The center hydraulic reservoir is in the right wheel well. The left is in the left engine strut, and the right reservoir is in the right engine strut. The left and right hydraulic systems each have their own fluid reservoir. Each left and right system is pressurized by a primary engine-driven hydraulic pump. The left and right systems also have an electric motor-driven pump that operates upon demand when the loads require an additional source of pressure. This frame shows the components that receive pressure from the left and right systems. The center hydraulic system provides the operating pressure to many important components and heavy load items. The center system has its own fluid reservoir. The center hydraulic system is normally pressurized by 2 electric motor pumps, but also has an air-driven pump that operates upon demand. The air-driven pump is driven by bleed air pressure and provides a backup pressure supply to the center system when the electric motor pumps have failed or are not providing adequate pressure. In the event of a dual engine failure, a ram air turbine or RAT is installed to automatically provide backup pressure supply to the flight controls of the center hydraulic system. Although the RAT deploys automatically in event of dual engine failure, a manual RAT deploy switch is installed on the overhead panel. All primary flight controls are hydraulically operated without manual reversion. There are 2 ailerons on each wing. They are the inboard and outboard ailerons. The inboards are always operable, while the outboards are locked out during certain conditions, such as high-speed flight. Each aileron is powered by 2 separate hydraulic systems. The elevators and rudder are each powered by all 3 hydraulic systems. The aircraft is equipped with an elevator feel system. Thus, at higher airspeeds, the pilot forces required to move the elevator are increased. There is no control switch for operation of this system. The aircraft is also equipped with a rudder ratio system. It provides enhanced rudder operation at slow speeds and inhibits full rudder throw as a function of airspeed. There is no control switch for operation of this system. The rudder is also equipped with 2 yaw dampers. Switches on the overhead panel are used to turn on/off the yaw dampers. The secondary flight controls are hydraulically operated. The secondary flight controls include the spoilers, flaps, and slats. The spoiler's speed brakes are extended in flight to increase drag and destroy lift as speed brakes. On the ground, the spoilers are extended during landing or RTO to destroy lift and add drag. The flight spoilers augment the aileron operation when the control wheel is rotated. This roll augmentation is available on the ground or in flight, whether speed brakes are retracted or extended. The slats have 3 positions: up, mid-range, and landing. The slat position is normally selected along with the flaps by use of the flap lever. The slats are normally operated hydraulically, but can be electrically operated when hydraulic operation has failed. This is referred to as alternate slats. Alternate slat operation is manually selected by the crew by use of a switch, and then the slat position is selected by a rotary knob. The flaps can be selected to any of the detented positions shown on the flap lever. The flaps are normally operated hydraulically, but can be electrically operated when hydraulic operation has failed. This is referred to as alternate flaps. Alternate flap operation is manually selected by the crew by use of a switch, and then the flap position is selected by a rotary knob. This frame shows the available and normal flap settings for takeoff and landing. Stabilizer trim is provided by one of two hydraulic trim systems. Trim is powered by the left and center hydraulic systems. There is no provision for manual trim, and there are no trim wheels installed. In addition, there is no aural tone that occurs during trim operations. A pitch enhancement system, or PES, is installed to provide a backup method of trim operation. Here, you can see the nose gear in the extended position. The nose gear retracts hydraulically and is held up by an over-center link. The nose gear normally extends hydraulically, but can be extended through free fall. The nose gear doors are mechanically opened and closed. They are closed when the gear is retracted. The nose gear retracts hydraulically. Maximum nose wheel steering is 65 degrees when controlled by the tiller. Rudder pedal steering provides a maximum steering angle of 7 degrees. Each of the main landing gear has 4 wheels on each truck. The landing gear normally operate hydraulically. Freefall is available as an alternate means of gear extension. Doors are attached to the main gear struts to enclose the struts and wheels after retraction. There are no gear viewers on this aircraft. Verification of gear extension or retraction is provided by gear lights, an amber gear light and associated ICAS messages for disagreement indications. The main gear wheels have hydraulically operated brakes with anti-skid protection. Normal, alternate, reserve, and accumulator brake systems are installed. For normal brakes operation, an auto brake system is available and is used for RTO and landing. The APU is located in the tail section of the aircraft. Inlet air for combustion and cooling enters the APU compartment from the aircraft right side. This inlet air enters the compartment through an automatic inlet door. APU exhaust is delivered straight out the aft end of the aircraft. The APU is equipped with a generator. It can provide all necessary electrical power when the aircraft is parked. With an inoperative engine-driven generator, the aircraft can dispatch with the APU as the second source of electrical power. Certain flight restrictions apply and are noted in the MEL. Although APU bleed air is normally used on the ground, it can be used to provide pneumatic air in flight, but only up to 17,000 feet. The APU has a ground control panel and fire warning horn on the nose gear strut. An APU fire control switch, bottle discharge switch, horn cutout button, red light and horn are installed on this panel. Ground personnel will use this panel to fight an APU fire when on the ground. The conventional ADI and HSI have been replaced by the electronic flight instrument system, which is referred to as EFIS. These displays provide a graphic image of the aircraft flight parameters and route information. The Boeing 767 instrument package is a flat panel display system with an ISFD, integrated standby flight display. The aircraft is equipped with 3 inertial reference units, or IRUs, that comprise the inertial reference system, or IRS. The aircraft is equipped with 3 flight control computers, or FCCs. These computers provide flight guidance and autopilot operation. Although normally only one autopilot can be engaged, the selection of the approach mode for landing will normally engage all 3 autopilots for a Land 3 capable fail-operational autoland. Pilot inputs to the FCCs is through the Mode Control Panel, or MCP, on the glare shield. A Flight Management System, or FMS, is installed that can be coupled to the autoflight system. The FMS provides guidance for lateral navigation and for vertical flight path. Each pilot can input and receive FMS information from a control display unit or CDU. To determine the aircraft position, track, and speed, the FMS uses the IRS position data and also derives position data by automatic tuning of the navigation radios. Some aircraft are equipped with a global positioning system or GPS for precise position determination. There is no GPS control panel, but if the aircraft is equipped, you can see the GPS position is displayed on the position initialization pages of the FMS CDU. The aircraft is equipped with two flight management computers or FMCs that comprise the heart of the flight management system or FMS. It is through the control display units or CDUs that the pilots enter and retrieve data from the FMS. The FMS can be selected to control the autoflight system for lateral LNAV and vertical VNAV flight by selection of the LNAV and VNAV buttons on the MCP. Selection of LNAV and VNAV are independent of each other. That is, one can be selected without the other. Use of the FMS LNAV and VNAV modes provide the highest level of flight automation and can be engaged just after takeoff and used throughout the flight. The engine parameters, system annunciations, and crew alerts are displayed on the upper and lower ICAS screens. You will find that 767 operation will require your understanding and use of the ICAS system. This completes your introduction to the 767. Detailed descriptions and fleet differences are provided in specific system modules.